Hello, this is Miss Moore, and today during chemistry we're going to talk about Lewis dot structures. Specifically, we're going to talk about the exceptions. So today's essential questions. What atoms do not follow the octet rule? Okay, exceptions to the noble gas configuration. Sometimes the atoms in a molecule do not achieve noble gas configuration when bonding. And there are two types of exceptions. The first one is what we call incomplete octets, which probably is self-explanatory. You end up with atoms with less than an octet of valence electrons after bonding. Think about boron and beryllium, and we'll try one in a moment. Okay, the next type is expanded octets. And these are atoms that end up with greater than an octet of valence electrons after bonding. All right, incomplete octets. Three common atoms that form incomplete octets are beryllium, boron, and aluminum. And the reason for that has to do with the number of valence electrons. So let's say we have boron. Boron has 3 valence electrons. That's it. So if we were to have something like boron trifluoride, you would end up with a structure like, I'm getting there, like this, where the fluorines all have an octet, but boron does not, right? Boron has 2, 4, 6. It only has 6. In this case, I guess, valence electrons after bonding. Okay, that's an incomplete octet. Expanded octet. Some atoms in periods 3 and on can form some compounds in which more than 8 electrons surround the central atom. So how about for an example, PCl5. Okay, phosphorus has 5 valence electrons, and the chlorines, I think I'm not going to draw all of them, have 7 valence electrons. So we're going to be starting with phosphorus, right? And so we have phosphorus, and then we have a chlorine that can attach to it. Well, the first 3 chlorines are easy, right? There. And then there, and then there. But we need 2 more chlorines. So what ends up happening is this phosphorus ends up sharing these paired electrons as well. So we end up with Cl and getting crowded. Let me get rid of this stuff. There we go. And Cl. Okay. So there's an example of an expanded octet. Okay, I want to try one more example with the expanded octets because they are a little funky. So let's try xenon tetrafluoride. So xenon is a noble gas, so has 8 valence electrons, and fluorine is a halogen having 7 valence electrons, and there are 5 of these. I'm just not going to draw out all 5. All right, so we're going to start with xenon in our center, and there's no obvious bonding spots. So what we're going to do is just start bonding them to, even though the electrons in xenon are already paired, we're going to still bond up. So and here. Oops, why am I putting FE? I have no idea. Let's try that again. There we go. Sorry about that. Okay, and you will note, so that's going to be the structure almost. We've still got to deal with xenon's other electrons, so I'm going to color those in yellow real quick. So xenon now has what looks like 4 unpaired electrons. But what we're going to do is we're going to pair those back up. So when you're drawing the Lewis dot structure, so I can erase these guys. We're going to take these, pair them up, so we'll have, there you go. So now xenon has lots and lots of electrons around him, way more than 8, right? We've got in the bonds, we already have 8, plus the 2 pairs. Now he now has 10 electrons around him. Or 12, sorry. Too bad I can't count. It's 12 electrons around him. Okay, so there is expanded octets. All right, and now let's go through a quick guide to the octet rule. How to tell when an atom is supposed to obey the octet rule, not general guidelines. All right, so the period 2 elements, carbon, nitrogen, oxygen, and fluorine, should be assumed to always follow the octet rule. Okay? And then we have the period 2 elements, boron and beryllium. These guys often have fewer than 8 valence electrons around them in their compounds, which makes sense because each of these only has, well, 3 or 2 valence electrons, right? 3 and 2. Period 2 elements never exceed the octet rule. So that's the general feeling. It could have an incomplete octet, but period 2 elements, or period 1 for that matter as well, will never exceed the octet rule. Period 3 elements and beyond, meaning period 3, 4, 5, etc., often follow the octet rule. In fact, more often than not. However, they can exceed the octet rule and the way they do that is by using their valence d orbitals. Not that you need to indicate that when you are drawing Lewis dot structures. You don't, but that's why. That's how it works. Okay, so here you go. When writing Lewis dot structures for a molecule, what you want to do first is what we learned at the beginning. Satisfy the octet rule for all the atoms. If electrons and atoms remain after the octet rule has been satisfied, then place the rest of the elements around, and what you'll be doing really is using the available d orbitals, keeping in mind that it's only period 3 and beyond that you can do that with. All right, that's it for today. Have a good one.